This is standard stuff. The advantage of this formalism is that because the background metric is rotationally invariant, the perturbations, of course, are not rotationally invariant, but to the extent that they're described by linear field equations, the field equations break up into uncoupled field equations for quantities according to how they transform under the rotation group. There is a set of field equations for the scalar quantities, which are phi and psi are, remember, the perturbations in the metric tensor, delta rho and delta p, the perturbations to the energy density and pressure, and delta u, the perturbation to the scalar velocity potential. And if you only have these satisfy a set of equations by themselves. These are called compressional modes. Zeta and delta uv, and I should have put also pi v, are the vector or rotational modes, and they're uncoupled to the others. And chi ij and also pi ijt, that's the tensor or modes, also known as gravitational radiation. As long as you work to first order, there's no coupling between the gravitational field for scalar, vector, or tensor. And of course, since the background is not only rotationally invariant, but translationally invariant, I'm assuming that in the early universe, the spatial curvature can be neglected, which is almost certainly a very good approximation, even if it isn't zero now. It was very small then. All the perturbations, all of them can be written, their space dependence can be expressed in a common factor e to the I q dot x, where q is a co-moving wave number. Q is not the physical wave number. Q divided by the Robertson-Walker expansion factor is the physical wave number. Q actually has no significance because it depends on how A is normalized, and only Q over A has a physical significance, but it's not constant. It changes because A, of course, increases. The universe is expanding. Very often people talk about a quantity K, which is just the value of Q over A at present. Now, the equations for the scalar modes, there are a lot more equations than these, but they can be boiled down to these, and these are really not so complicated. There's a gravitational equation for phi and psi, remember, are the scalar components of the metric perturbations, and on the right-hand side is a sum over all fluids of the unperturbed rho plus p, indicated by a bar, which you may not see, times the velocity potential perturbation for that fluid. Each fluid satisfies an equation of the conservation of momentum with a time derivative of the velocity potential and a conservation of energy with a time derivative of the energy density. There is also an equation that eliminates one of these two potentials. There really is only one independent scalar potential for the gravitational field. The difference between phi and psi would vanish if there were no anisotropic inertia, and with anisotropic inertia, it's proportional to the anisotropic inertia. And in addition to these equations of motion, there is also a constraint which doesn't involve time derivatives and can be imposed at t equals 0 or any time you like. And the field equations tell you it's constant. So once you impose it as an initial condition, it remains true. Those are the scalar equations of motion. And there's the tensor equations of motion, you'll be glad to hear, are much simpler. It's just a simple wave equation for chi, the gravitational wave field, with the right-hand side being a sum of the tensor parts of the anisotropic inertia for all the fluids. By the way, you may notice here that I've missed an opportunity to cancel the qi, which appears on both sides of this equation, and to cancel the qi, qj, which appears on both sides of this equation. I left them, this is the way the equations occur directly by putting the ansatz for the perturbations into the Einstein field equations. And of course, the natural thing would be to cancel the q's here. I'm not going to, for a reason that you'll see very soon. Now, as I said in the introduction, the question is, how can you connect the fluctuations that arise during inflation with those observed now, when a great many things happened in between about which we know very little? And especially here, I'd like to think of the reheating of the universe at the end of the period inflation, about which we not only know very little, but we know nothing at all. We have no idea how that happens. How can we reliably connect the period of inflation with the present, then, when you have intervening epochs that we know nothing about? Well, the clue is that there is a conservation law that holds outside the horizon. Let me explain that expression, outside the horizon. Inside the horizon means that the physical wave number is large compared to the expansion rate, which I generally just call h, a dot over a. And outside the horizon means the physical wave number is small compared to a dot over a. It's a bad nomenclature because the actual horizon is much larger than 1 over the expansion rate. It would only be of the order of 1 over the expansion rate if there were no inflation. The whole point of inflation is to expand the horizon. And this is what's really meant. But I think anyone who's ever had experience with solving an ordinary differential equation knows that if the physical wave number is large compared to the rate at which things are changing in the equation, then you can solve the equation to a certain approximation by treating the background as static. Whereas on the other hand, if the physical wave number is very large compared to the rate at which the background is changing, you can treat the equation by kind of WKB method. And that's what distinguishes these two. Now, when are you inside the horizon? When are you outside the horizon? Well, here I've plotted a dot over a and q over a. During the period of inflation, a dot over a is roughly constant. Not exactly, but it doesn't change very much. And then at the end of inflation, when the energy that was in the vacuum gets turned into heat, a dot over a starts decreasing the way it does in an ordinary cosmology, like 1 over t. A dot over a is it's 1 over t, whether the universe is radiation dominated or matter dominated. On the other hand, q over a, q is constant, but a is exponentially increasing during inflation. So originally q over a was very large compared to the expansion rate, but at a certain point it becomes less. That's called leaving the horizon, or going outside the horizon, because at this point you begin to have a dot over a large compared to q over a. And then at the end of inflation, a stops exponentially increasing. It begins to increase like t to the 2/3 for a matter-dominated universe, or t to the 1/2 for a radiation-dominated universe, and it begins to fall off much more slowly, and in fact more slowly than a dot over a. So they cross again, much closer to the present. So there are 3 crucial epochs that you should keep in your mind. In fact, this is the most important figure, I think, in all of theoretical cosmology. There is the period of horizon exit, which occurs during inflation. There is the end of inflation, and there is the period of horizon re-entry, which is the beginning, if you like, of modern times. The important thing is that this mysterious epoch, the epoch of reheating, occurs when the horizon is way outside the when the perturbation wavelength is much larger than the horizon size, that is, the wave number is much less than the expansion rate. And so we have a hope of understanding, we have a hope of connecting what happened here with what happens here if we can find a conservation law that holds when you're outside the horizon. Because almost all the things that we don't understand, grand unification, symmetry breaking, reheating, almost everything that is mysterious to us happens when the perturbations that we study today, the ones that are studied in that map picture I showed you at the beginning, when those perturbations are outside the horizon. So is there a conservation law outside the horizon? Well, it depends. Lots of people have found that in special cases there is. There is a quantity, and I'm going to work with one quantity. All the other quantities are equivalent in the sense that they all become equal to this or simple functions of this when you're outside the horizon. So there's no point in arguing about which one you want to study. There's a quantity script r, which is defined as minus psi. Remember, that's the scalar part of the gravitational perturbation, plus h delta u. H is the expansion rate, delta u is the perturbation to the velocity potential. This was already introduced by Bardeen in 1980. And r is constant outside the horizon in a number of special cases. For a single fluid where the total pressure is some function of the total density, as for example, if you have a massless fluid, then the total pressure, including the perturbation, is just 1/3 the total energy density, including the fluctuation. Then r is constant outside the horizon. And also, if you have inflation with a single inflaton field, then r is constant. For the tensor modes, one really just has to look back at the equation of the field equation for the tensor modes. If you're outside the horizon, this term is negligible, and if you don't have any anisotropic inertia, which in many cases you don't, then the equation just becomes chi double dot plus 3h chi dot. That has a solution where chi is constant, chi dot is 0, and it also has another solution where chi dot goes like 1/a cubed, so although it may not be constant, it rapidly becomes constant. So there is a conservation law outside the horizon. Now, but these are very simple special cases. What can you say in general? And I think now I'm coming to my own work. So far, everything has just been review. I think this is the only attempt to really deal with this in general terms. There is a theorem, sort of half published in one reference and then half in the other, that whatever the system involved, there are always two scalar modes with r constant outside the horizon. One of them with this quantity r not equal 0, and the other with r equals 0. Obviously, if there are two modes with r constant, you can always define one of them to be the one with r equals 0. And also, there's another theorem that there's always a tensor mode. As we saw in the simple case where there's no anisotropic inertia, there's always a tensor mode where chi ij is constant outside the horizon. That's not so trivial because remember, when the neutrinos decoupled at a temperature of about 10 to the 10th Kelvin, the universe was very viscous, and there was a lot of anisotropic inertia. And the argument I gave you does not apply, the simple solution of the field equation that I gave you. But nevertheless, the theorem says there is, even at such times, when you can't ignore the anisotropic inertia, there's always a tensor mode with chi ij constant outside the horizon. The proof is essentially a recycling of Goldstone's theorem into a somewhat different context. It makes use of the fact that well, first of all, if you're outside the horizon, that means Q over A is negligible. So you can study the problem by setting Q equals 0. That's not exactly true. I'll come back to why it isn't exactly true, but let's consider Q equals 0. In that case, all field equations and the condition Q equals 0 are invariant under a group of transformations, and these are the most general transformations that leave the field equations and the condition q equals 0 invariant. You can translate the time by an arbitrary function of time, and you can subject xij to an arbitrary infinitesimal linear transformation. It doesn't have to be a rotation, just an arbitrary linear transformation that's infinitesimally close to 1 will do. But unless wij is antisymmetric, which would make this a rotation, this is not a symmetry of the unperturbed metric. And that's the classic situation where you have a Goldstone theorem, where you have equations, or whether they're field equations or whatever, that have a symmetry, but the unperturbed solution, in particle physics we talk about the vacuum, doesn't share the symmetry. Then you get modes. Well, in particle physics we would say massless modes. Here we would say you get modes with q equals 0. And the way you prove this is just to perturb the unperturbed metric, that is the Robertson-Walker metric, by making these coordinate transformations. The perturbation, when you take the ordinary Robertson-Walker metric where g00 equals -1 and make this transformation, you get a term plus epsilon dot of t. And when you make this transformation, you get a term gij equals a square of t. You get a term involving epsilon of t, but you also get a term involving the symmetric part of omega ij. Well, this just looks like the perturbations that I defined on the first non-trivial view graph, which I think it's hopeless to find now. But if you go back to that view graph and you remind yourself of the definition of phi and psi and chi and all those things, you can see that this metric is just of the same form that we had before, but where psi is given by h epsilon minus 2/3 the trace of omega, and phi is minus epsilon dot, and chi is just the traceless symmetric part of omega. Now, at this point, one is tempted to say, so what? All one has done is taken the Robertson-Walker metric, made a coordinate transformation, and found a perturbation. That is what's known in the trade as a gauge mode, and it is supposed to have no physical significance whatever. And that is normally true. But this symmetry of the metric only exists for q equals 0. For q not equal 0, which is the true for any perturbation that we're going to study, however small, there are no symmetries of this type. And this, if it can be extended to q not equal 0, becomes a physical solution. So the question is, can this be extended to a solution for q not equal 0? You see, when you're way outside the horizon, it's a very good approximation to take q equals 0. But q is not really 0 for the perturbations that we observe. As you come back into the horizon relatively recently, maybe around the time of recombination, q returns, and you're observing perturbations now that have a completely non-negligible q. So the interesting thing is not what happens at q equals 0, but what happens outside the horizon when q is very small, although not precisely 0. Now, in general, these are not solutions for q not equal 0. I mean, of course they're not solutions for q not equal 0 because they were only derived for q equals 0. What I should have said is that they can't be extended in general to solutions for q not equal 0. And that's because when I wrote the equations of motion, there were two equations that had factors of q in them. If you set q equals 0, these equations disappear, and then of course you can solve the others, and that's what this has done. But if you want to be sure that the solutions can be extended to q not equal 0, then you have to impose additional conditions to the q equals 0 solutions you found, namely that the coefficient of q here is equal and the coefficient of qi, qj here is equal. In other words, you must impose the condition, well, I'll do it one at a time. First of all, you must impose this, which had a factor qi on both sides, You must impose the condition that this is 0. If you insert the value psi equal h epsilon minus 2/3 the trace of omega here, of course that term goes out, it's a constant, and phi equal minus epsilon dot here, then this becomes just the time derivative of h epsilon minus h epsilon dot, which it's not hard to figure out is just h dot epsilon. On the left-hand side, you have h dot delta u. So the condition that has to be imposed is just that delta u is epsilon. If you impose the condition that delta u is epsilon, then the quantity r, this conserved quantity which we're concerned about, which is defined in general as minus psi plus h delta u, the varying terms cancel. Psi, remember, is just h epsilon plus minus 2/3 of the trace, so you have minus h epsilon here, and then that's canceled by h epsilon, because delta u is just epsilon. And all you have left is just 2/3 the trace, which is a constant. So such a mode is indeed one where r is constant. And the other condition that has to be imposed is this condition that relates phi and psi, which you can do whether or not there is anisotropic stress present, and that condition then gives you a differential equation for epsilon. So you can not only show that there is a solution where r is constant, but you can even find out exactly what that solution is in general without knowing anything about the equation of state or whatever. Epsilon is just given by this, and when you plug that in here, that tells you what delta u is, and it tells you what psi and phi are. So the solution is known. There's an integral dt over a of t. The integration constant here is a second mode. Since the value, the integration constant in epsilon doesn't affect the value of r, that's the second mode with r equals 0. For tensor modes, it's simpler. For tensor modes, I proved on the previous view graph that there is always a solution in which chi is constant, and there are no terms involving q in the field equations that require me to impose additional conditions to extend this to q not equal 0. So this proves the general theorem, which means that we can very often tell whether or not, now I'll show you in a minute that r can be calculated from what we know about inflation, and it can be used to calculate things like the curve for CL versus L that I showed you in the very first view graph. So knowing that r is conserved for the scalar modes is just what you need. And knowing that chi is conserved outside the horizon, conserved, I always mean conserved outside the horizon, is just what you need for the tensor modes. Let me just mention a few cases where r is conserved. And it turns out to be just a matter of counting, which is good because I know how to count. For real scalar fields with a potential v of phi, the scalar field is written as an unperturbed term plus a perturbation. The unperturbed term satisfies a second-order differential equation. This is famous. It just represents a ball rolling down the hill. The h is like a viscous term, but it's just the expansion rate, which is given in terms of phi dot and v of phi. That's standard stuff. Well, in fact, up to a certain point, it's all standard. These also are well known, the perturbed field equations. There's no anisotropic inertia for the theory of scalar fields, so phi equals, capital phi equals capital psi. This is the gravitational field equation. This is the field equation for phi. And there's also that extra constraint, remember. If you look at these field equations, there's one time derivative there and two there. So this is a third-order system of ordinary coupled differential equations, and therefore has three independent solutions. So at first that looks pretty bad, but there's a constraint. which involves only the initial data, phi, phi dot, and psi, and that constraint reduces the number of independent equations to 2. What it does is tell you one of the 3 solutions isn't there. And so there are only 2 independent solutions. But I just proved to you that there are always 2 independent solutions with R constant. And since there are only 2 independent solutions, it follows that R is constant. This is not a difficult chain of reasoning. When I say constant, I always mean constant outside the horizon. Another case where it's equally easy to draw the conclusion, is, I don't have a view graph for it, but I'll just tell you, when you have a single fluid where P is simply a function of rho, and delta P is the same, well, P plus delta P is a function of rho plus delta rho, then there really is only, there are, again, essentially only 2 equations, 2 solutions, and so therefore R is conserved. Now, so that's what you have to do facing any particular model, say, of reheating. You have to look at it and say, how many solutions are there? If there are 2, no more than 2, you're finished. If there are more than 2, then you have to ask, are the additional solutions for which R is not conserved actually excited? If they are excited, even if they decay away, they will change the value of R from what it was produced in inflation to what we see now. And therefore, they invalidate a lot of the predictions of inflation. Let me just say something about how you use the current value of R. And now again, I'm giving standard results. R is a function of x and t. It can be Fourier transformed, as I indicated. These B's, early on you should think of them as quantum mechanical operators. Later, in a mysterious way, which maybe I'll say something about, they become stochastic variables, but they're normalized in either case, so the expectation value of BB star is just a delta function. And that leaves RQ of t as an ordinary C number function of time that you have to compute. That's the physically interesting thing. The correlation function of something that depends linearly on R will involve, obviously, absolute value squares of RQ of t. Outside the when you study inflation, this again is a well-known thing, I have nothing new to add, you find that the value you're left with outside the horizon in the theory with a single scalar field is just given by conditions at the time of horizon exit. It's given by this formula where HQ is the value of the expansion rate at the time that Q over A is of the order of H. H is A dot over A. So it depends on Q, but if the potential is nearly flat, it depends very weakly on Q. Phi Q bar dot is the rate of change of the unperturbed scalar field at the same time when Q over A is of the order of H. It depends on Q also, but again, if the potential is flat, it doesn't depend rapidly on Q. And then there's a famous Q to the minus 3/2 that actually fits that curve I gave in the first view graph. And there's an intense effort to find these additional factors which modify the Q to the minus 3/2. But of course, the question is whether this formula is right, whether or not this is the formula you should use when the perturbation is ready to re-enter the horizon. Similarly, for the gravitational waves, again, you expand them in normal modes, and you get, these are polarization tensors, these are stochastic variables normalized to a delta function. Chi Q of t is the envelope of the gravitational wave. That's not the envelope, it's the time-dependent part of the gravitational wave. and the value outside the horizon in simple theories of inflation where you have a single scalar field is just given by the expansion rate at the time of inflation, at the time of horizon exit, divided by the same q to the 3/2 and with different numerical factors. Well, that's what inflation tells you. Now, how do you use that value of r and chi at the present? Well, this is a big subject which I don't have time to go much into, so I'll just race through some view graphs. The simplest case is where you're dealing with fluctuations that have such a long wavelength that they don't re-enter the horizon until after the time of recombination or last scattering of the microwave radiation background. In other words, they re-enter the horizon at a redshift less than 1100. These are the fluctuations that determine CL when L is less than square root of 1 plus ZL, where ZL is the redshift at last scattering, and that's about 33, because ZL is about, well, it's actually 1090. So these low values of L, these are the values of L that were first studied by the COBE satellite in 1992. For these, there's a very simple result, which is that the fractional perturbation to the temperature in any direction is just given by the value of r in that direction with a factor 1/5, which is what you have to calculate, but it does come out to be that. And what that tells you is that when you expand the correlation function of the temperature, you just get the Fourier transform of the absolute value of r, q. The O stands for outside the horizon. It's not a 0, it's an O, meaning outside. And that's what's set equal to the Legendre expansion. And if for this, you just put the very simple b q to the minus 3, which is what you get for a potential which is very flat at the time of horizon exit, then you can easily calculate this integral and compare it with the Legendre expansion and figure out that CL is just 8 pi squared b times L plus 1 over 25. That L times L plus 1, that's why in graphs, when the data is presented, they always give you the data for CL over L times L plus 1. I'm sorry, that should be divided by L times L plus 1. And what they always give you is CL times L plus 1. But anyway, the result is that the thing which is measured in COBE, which is CL for low L, gives you the value of this B in the form 8 pi squared B over 25 is 778 microkelvin to the minus square, not to the minus 2 square. So this is a very simple example of how knowing the value of r outside the horizon tells you the magnitude of the multiple coefficients of the perturbation correlation function, in this case for low L. This is the experimental result, 778 microkelvin to the minus 2. For larger values of L, where the scalar fluctuations re-enter the horizon, I don't have much more time. I'm going to skim this. Before last scattering, it's more complicated. For L less than 300, horizon re-entry occurred during the matter-dominated era. I've studied this myself in some papers we referred to here. It's been I think this is the most thoroughly analytical treatment, but of course this has been studied to death by a great many other people and is now done by computer. The other people who have done this analytically, Hu, Doddleson, Mukhanov, he calls it CMB slow in contrast to the CMB fast computer program. For L greater than 1,000, horizon reentry occurred during the radiation-dominated era. That's been studied analytically by Hu and Sugiyama and by myself. The results there, my results are that the fractional density perturbation in the dark matter is given by this formula, where again, I think the only thing I want to bother pointing out is that r outside the horizon enters as a factor in the perturbation. And this allows you to calculate something called the transfer function, which I won't go into. Now, what I'm really interested in here is asking the question whether you can believe all this, and whether you can believe that the value of r, which we're measuring today, is related to the value of r that was produced by fluctuations during inflation. Can you use those formulas I gave you for what r is outside the horizon in terms of the Hubble constant and the rate of change of the scalar field at horizon exit? Well, one thing that happens between horizon exit and the present is reheating. And I don't think this question has been studied before, and I've just begun, actually, in preparing for my talk here, to study this, so I'm just beginning with this. And I took the very simplest example of a theory of reheating, which you can find in the book by Kolb and Turner. You have inflaton, well, the potential is imagined to be slowly decreasing. That the unperturbed scalar field, remember, rolls down viscously down the hill. And then, for some reason we now don't understand, which undoubtedly the string theorists will tell us by and by, the potential becomes just a simple harmonic well, which looks like a mass term in the Lagrangian, 1/2 m phi square, phi minus phi 0 square, where phi 0 is the location of the minimum. And the potential in this well rocks back and forth. The expansion of the universe causes the amplitude to decrease, but also, if the scalar field is coupled to other matter, its energy is transferred into the other matter. And you can think of it as massive inflatons with mass m phi simply decaying into the other matter. The simplest case is where the other matter is thermalized relativistic decay processes. In other words, radiation, if you like, but which becomes immediately thermalized so that it has a simple equation of state. The pressure is 1/3 the energy density. Whereas the inflatons behave like cold dark matter now, although they're decaying, so they're not the cold dark matter that we see today, with zero pressure and the energy density, which is just the mass times the number density. Now the equations, the unperturbed equations, are extremely simple. Rho dot is minus 3h rho, which is the usual dilution of a number density due to the expansion of the universe, but with an extra term representing the decay. Gamma is the decay rate of the inflaton. Rho dot, that's for the inflaton energy density. For the radiation energy density, rho dot is minus 4h rho phi. It's a 4 rather than a 3 because you have pressure as well as energy density. And now plus gamma rho phi, because it's gaining energy from the decay of the inflaton. Those are the unperturbed equations. The perturbed equations are not so simple and involve the gravitational field. But when you're way outside the horizon, they still take a fairly simple form. These are the perturbed equations for the fluctuations outside the horizon. They depend on psi dot and psi in this way. And at first I dropped this last term and got nonsense, but then I worked back, and general relativity requires this last term to be there. And you also have a gravitational field equation. So you have 3 coupled first-order differential equations for 3 unknowns, delta rho, delta phi, well, delta rho phi, delta rho radiation, and capital psi. And so there are 3 modes. You know, without thinking about it, one of these modes has r constant and not 0. That was the theorem. Another mode has r constant and 0. But there is a third mode. And if that third mode is present, if there's a third solution, then you're in trouble, because then r is not conserved at the time of inflation. Now, the way to get the initial conditions is really to do this right and go back to the quantum fluctuations in these photons or neutrinos or whatever they are at the beginning and work out what rho r is and rho phi is by solving the problem inside the horizon. I haven't done that. But just to show the possibilities, if you say that at the beginning of reheating there's no radiation, rho, the unperturbed, and the perturbation to the rho r are both 0, then you can show that in fact r is not conserved at this instant at the beginning of reheating, and in fact you can calculate what r is, and it's well, probably gamma is large compared to h, because otherwise this picture doesn't make much sense. So this is essentially minus gamma square over 9h. And if you say that this is roughly true for a time of order 1 over gamma, then you find that r dot over r is, that r changes by a fractional amount, which is of the order of gamma over h, which we're assuming is large. So this suggests that in fact, simple theories of reheating can produce very large changes in r, invalidating the, certainly not invalidating all of the theoretical work that goes into comparing the microwave background fluctuations with experiment, but invalidating that part of it which has to do with calculating the properties of the inflation, especially calculating the energy density or the Hubble constant during inflation. The last thing I want to talk about in the remaining 10 minutes is what happens to the tensor modes when they re-enter the horizon. This is something I've been working on for a while. In most review articles, there's a simple statement that the tensor modes are unaffected by matter and radiation, and therefore you can simply calculate using that very simple wave equation that I had on an earlier view graph, which I know by heart, which says that chi double dot plus 3h chi dot plus q square over a chi equals 0, and ignore the anisotropic inertia term, which is on the right-hand side of the equation. Well, that's fine during most of the history of the universe. During most of the history of the universe, in particular during inflation and during the radiation-dominated era, the universe was essentially a perfect fluid. But there are times when it wasn't, in particular when the neutrinos, once they decouple at a temperature of 10 to the 10th, when these perturbations are way outside the horizon, are then free streaming. And that gives an anisotropic inertia when you have particles that aren't colliding rapidly with the others. So what I did was try to calculate the damping of tensor modes that's caused by the anisotropic inertia term on the right-hand side once you come back into the horizon, which occurs long after the neutrinos decouple from the rest of the universe. Now, you can solve the Boltzmann equation to find out what that pi is, and the thing which appears in the equation for chi q, the simple chi, is just given by that formula. I need the pointer, don't I? It's given by that formula, where k is a very simple kernel, it's this, and z is just a function of time. It's just the so-called conformal time times the co-moving wave number. So that tells you what this pi is, and the problem is to solve this differential equation. It's much more convenient, instead of working with time, to work with a quantity called y, which is the ratio of the Robertson-Walker factor to the value it has when radiation and matter give equal contributions to the energy density of the universe. That differential equation is here. This is the left-hand side that you would have in any case, and this is the part that comes from the neutrinos producing an anisotropic inertia. And F nu is the ratio of the unperturbed energy density of the neutrinos to the total unperturbed energy density, which we believe is 0.40523. That's something that's very accurately known. And the kernel is the same kernel it was before, except with the argument S now expressed as a difference of, well, in terms of y and y prime in this way. And the only parameter in everything here is independent of any cosmological parameter except capital Q, which is can be written as the wave, square root of 2 times the wave number. Well, it's better to look at this expression. It's the wave number at present, which is Q over A0, divided by the Hubble constant, and then this function of cosmological parameters. You can also look at it this way. Q equilibrium, not equilibrium, Q equal is the wave number that's just coming into the horizon when radiation, including neutrinos and matter, have equal energy density. So in other words, Q large compared to 1 means that the perturbation comes into the horizon during the radiation-dominated era. Q small compared to 1 means the perturbation comes into the horizon during the matter-dominated era. Q equal 1 means that it comes into, well, actually, Q equals square root of 2 means it comes into the horizon just when they're equal, when radiation, including neutrinos and matter, are equal. The temperature and the polarization multipole coefficients of order L depend chiefly on the gravitational field perturbation through a factor which is just the time derivative, or you could take it the derivative with respect to y, of chi at y having the value it has at last scattering, which is just the ratio of the redshift at radiation matter equality to the redshift at last scattering. And the value of L that you have to take here is approximately the angular diameter distance of the surface of last scattering times the physical wave number at present. And if you take standard cosmological parameters, I won't go into why we believe all these, L is about 105 times capital Q. Nothing else in the problem depends on any assumptions about cosmological parameters. But if you want to convert this capital Q into an L, which is the label on the multipole coefficient, CL versus L, for example, in that first view graph, then you have to know these cosmological parameters. And roughly L is 100 Q. Now, a numerical calculation, a numerical solution of this equation, which is just an ordinary integral differential equation, Mathematica can't solve this kind of equation, I'm told by experts at Mathematica, but you can solve it as a perturbation series in F nu, which turns out to converge very rapidly. There's a graduate student, Matt Anderson, who knows about harder things like Fortran, and actually solved the equation directly for me, and our results agree. So I have some confidence in the numerical results. The numerical result is that all of these effects, temperature and polarization correlation functions, are damped by 8.99% for L much less than 100, or in other words, Q much less than 1, which is worth paying attention to, but not spectacular. Whereas for larger Q, for Q much larger than 1, damping reduces these effects, these temperature and polarization multiple coefficients, by 35.6%. These numbers, 8.99% and 35.6%, are independent of cosmological parameters, and can be, I can give them to you to 4 decimal places. The only thing where you have to know the cosmological parameters is in this conversion. And that's a very significant effect on what is expected. So, but even, I have to admit to you that the experimentalists are first going to do the observations for L less than 100 or about 100, where the damping is not a tremendous effect, it's about a 9% effect, but it's still something that should be taken into account. At one time, I thought it was a much larger effect, and unfortunately, the numbers come out this way. Actually, it's more complicated than that. This factor, the derivative of chi at y at the time of last scattering square, which gives you the effect on all these correlation functions, has a much more complicated graph. This is the graph. Actually, I wanted to show you the graph of the square. This is the very last view graph, so I'm not out of time. This is the graph of this factor versus Q, and you see the damping gradually increases. Here's one where there's no damping, and it goes from about a 9% damping to about a 36% damping down here. But these spikes that interrupt it, they're actually kind of fictitious. What you have is you're taking the ratio of two oscillating functions, one of which is chi as a function of Q if you include the damping, the other if you don't include the damping. And including the damping shifts the zeros of these functions. So this is just the ratio of two oscillating functions with slightly differently located zeros. And that's why it goes up to infinity and starts again at 0 and goes up here. Those places where the spikes are not places where the experiments are going to be done, because the places where chi prime is nearly 0 is precisely the places where you can't observe CL. So what's going to be done is to observe it first around here, and then maybe around here, and then maybe around here, and so on. And I hope someday around here, but we'll see. I think the most important thing I want to leave you with is that, well, first of all, you shouldn't believe everything in the astrophysical literature, which is the complement of the fact you can't understand everything in the astrophysical literature because a lot of it simply makes no sense. And when you do understand it, it's often wrong. But I think aside from those mordant comments, there's a positive thing, which is that I think it's really important to start thinking about various cosmological models, especially models of reheating, with an eye to telling whether or not in these models there is a quantity R, which is, well, there always is a quantity R which is conserved for some solutions, but do these other solutions which don't conserve the quantity R actually exist? And as far as I can see, they do exist in any reasonable model of reheating, and that makes it necessary to rethink some of the things we thought we knew about inflation. But the subject is wide open if anyone wants to work on it. Thank you.
Thank you very much.
I'm happy to take questions.
Being in time and other things. Are there any questions? Yes.
When you prove your theorem, you work in the longitudinal coordinates.
Yes.
But you also had some argument in the same direction using the synchronous case.
Oh, yes. You know, you've actually read something I wrote.
Yes. What I didn't understand in the...
I'm still confused about that. In the synchronous coordinate system, it looks like there's a conserved quantity in all cases.
Right.
And that's obviously a fallacy, but it's rather subtle. It has to do with what you mean by taking Q going to 0, or in other words, being outside the horizon. And I think the results in Newtonian gauge are more reliable. I think what happens is that in synchronous gauge, there are singularities at Q equals 0 that are not obvious. But if you start with solutions in Newtonian gauge which are not singular at Q equals 0 and then transform them into synchronous gauge, you find singularities at Q equals 0. Well, you might say, why should you believe one rather than the other? And I don't really have a good answer to that.
The point which puzzles me is also that if you go in synchronous gauge, there you can include spatial curvature. But here you start with...
Well, yeah, I don't know. I didn't even try to include special curvature, so I don't know anything about that. Thank you. What is your name? Okay, good. Well, I hope you clarify that, because I'm still puzzled by that. Another question?
Any other difficult question?
That was a gratifying question. Yes, Paul.
Steve, you gave an example where the reheating doesn't conserve R, or there are modes. Are you implying, are there any simple models of reheating?
Well, there are actually, what I find is that there are a lot of extremely Baroque models of reheating. Kaufman, K-O-F-M-A-N, and his collaborators have developed a theory of reheating where you have an additional scalar field, and instead of the universe thermalizing immediately, the energy of the inflaton field goes into this other scalar field, and then later, in a way which is not yet covered by him, you get real thermalization. In that case, the subject is much more complicated, and I don't know the answer there. I think there's been a little bit of a study of what happens to fluctuations there by Brandenberger and a colleague. I just saw a paper by Brandenberger yesterday, actually, which deals with this, but only in this very complicated case. And what I think is true is that the simplest picture, where you have immediate thermalization of the decay products of the inflaton, has never been studied beyond the 0th order perturbation, where everything is uniform and there's no metric perturbations. The fluctuations around that have never been studied, as far as I know. And it seems to me that's the most natural thing. If you're going to, eventually the universe has to thermalize, so the simplest is to assume it thermalizes then. It's much more complicated, as in the papers by Kaufman and other people, if you assume the universe does not thermalize then.
I have a question myself.
Yes, sir.
The quantity Q, which is
big Q or little q?
The small q, much bigger or much smaller than the rate of expansion, depending on whether you're outside or inside the horizon.
It's Q over A.
Q over A.
Yeah.
Is the fact that you take it to be sometimes much bigger and sometimes much smaller, is it an approximation that implies that the results are not very good in some cases?
No, no. I mean, well, it's never. I mean, certainly because A expands exponentially, it becomes an exponentially good approximation. Very early, when you go back to near the beginning and you want to study the quantum fluctuations that start the whole thing going, there Q over A is enormous compared to the expansion rate. And essentially, it's like the present universe. And when we study quantum field theory in the present universe, we ignore the gravitational field of the universe. We just work on what's happening in our laboratory. And that's an approximation, but it's a very good approximation. And so that's how you start. You start with a kind of principal equivalence, saying that when you're dealing with wavelengths very small compared to the local Hubble scale, the Hubble scale at that time, you can ignore the cosmology and just think of it as working in Minkowski space. Then after horizon exit, at the end of inflation, the universe has expanded at least 60 E-foldings. So Q over A is less, or 10 foldings, I forget which. But Q over A is like 10 to the minus 60 of H. And so it's a very good approximation to start with Q equals 0. I mean, there are, of course, corrections, but they're very, very tiny. Later, as the universe evolves, Q over A decreases and the Hubble expansion decreases, but the Hubble rate decreases faster, so eventually Q over A begins to be big compared to H again. And certainly at that time, you have to include them both. And that's what's done in conventional cosmological studies of fluctuations close to the present.
Any Any other questions? Apparently not, in which case let us thank Steve once again.
Thank you.